All right, so we're taking a look at magnetic fields, right? So in this magnetic field, of course, we do about so many things on CSEC, like Fleming, left hand rule, right hand rule, all those little things, right? We're going to take a look at how to find a new quantity called magnetic flux. It gives you an idea of how strong the magnetic field is. We'll take a look at current carrying conductors in a magnetic field, right? How they behave and how we calculate it, how we can calculate forces on them. And anybody remember how to get a direction? If you place a current carrying conductor in a magnetic field, right, left hand rule, right? Right? Three fingers, right? Someone gives it 2 and 1. Three fingers. Right? So we're gonna take a look at finding the strength of those forces. And we're gonna take a look, of course, run through the motor, take a look at magnetic induction, right? And a little bit of transformers, right? Yeah. Right, so it's very similar to what you would have done in CSEC, but of course we go in a lot more in depth, right? All right, ready? I have to draw some diagrams, right? Okay, so let's start. Before we do anything, we know about a simple magnet, right? That's magnetic field. That's right after. That is right after your. After the last level, we just did the potentiometer. After the Newton, the potentiometer. Right. A simple bar magnet has what? So a north and a south pole, right? Has a north pole and a south pole, right? Us. What is C? Right. And around the magnetic field, around the magnet, what do we have? A magnetic field. A magnetic field move from where to where? Magnetic fields leave the north and go towards the south. Right? That's a simple diagram showing magnetic fields and so on, right? So a magnetic field is defined as a region where a force is experienced. Does that sound familiar? That definition? A magnetic field is a region around a magnet where a magnetic force is experienced. Does it sound like anything? Well, does it sound like an electric field? Same definition, right? So what you will recognize that a lot of things that we did in electric fields get kind of applied here. Not everything, but most of it. Right? So a magnetic field is defined as a region where a force is experienced, for example, a region near a permanent magnet or current carrying conductor, right? For those who don't remember, around the current carrying conductor, we have magnetic fields. Okay? Right? And we represent current carrying conductors like this or like this. Anybody remember what the X represents? X is into the paper. Dot is what? Out. What is the rule I used to find the magnetic field around them? Right? The right hand grip rule, right? So the right hand grip rule, thumb points towards magnetic field. Thumb points towards magnetic field. And your fingers point towards the direction of the current. All right? Just do me a favor. Do me a favor and tell me what direction the magnetic field is. What direction the magnetic field is around the dot and the X. Just tell me clockwise or anti-clockwise. Right? So when the current coming out, it is counterclockwise. Right? You know to have this diagram. Let's see that and see, right? And the X is clockwise. Okay, let's catch them back quick. The rule is the right hand, right? right hand grip rule. Benaya, get them quick. Right, that's the magnetic field around a conductor. Good. All right, nice. Nice. So magnetic field is represented by magnetic field lines whose direction at a point gives the direction of the field. The direction of the field is taken as the direction, the force of the force exerted on a free node, right? So all it's saying is this. If here is north and here is south, right? And I place an object here, right? Of a magnet, the direction is given by, so if I place a north pole, if I place a north pole here, direction is where? So what's away from it? Away. Right. If I place a north pole here. So what? Towards here. Towards, right? So magnetic fields away from the north towards the south. Okay? That's what this is saying here, right? So if a free north pole is placed, the direction that that free north pole will move is the direction of the magnetic field. All right? Nice. Note that magnetic field pattern, magnetic forces, and well, separation, the greater the force, right? So what he's saying is this. Closer the magnets are, the smaller the force, and so on, right? All right. Before I jump into this, I want to just go over something. Right? But let me ask you also. Suppose I gave you a magnet, right? North, south, and I put a current carrying conductor. Sure in mind, right? Sure. Yeah, quick question. Yeah. What would happen there? If you like, don't sit on it. I will tell you the top, yeah, question. If I place a current carrying conductor in a magnetic field, what just normally happen to that current carrying conductor? Because okay, well, the conductor has a magnetic field and the magnetic field and the magnet is a magnetic field, right? But what happens to the conductor? Okay, so what has happened when two magnets interact? They either attract or repel to experience a force, right? So that current carrying conductor there, the little dot and circle. That's this current carrying conductor. That current carrying conductor should what? Experience a force, right? Right. So the direction of that force is given by Fleming's left-hand rule. All right. So I'll draw it here for you. Fleming's left-hand rule. If this thumb is the force, your first finger is the magnetic field direction, and your middle finger is the current direction. Okay. Right. So remember, this is Fleming's left hand rule. Right? So the thumb is the direction of the force. That's what we're trying to find. The first finger is the direction of the magnetic field. And the middle finger is the direction of the current. Alright? So let's do my favor and apply it to that small diagram there, that diagram one, and tell them what direction the force is. If you're taking a note, write down Fleming's left hand rule. Right? Fleming's left hand rule. Fleming's left hand rule. Fleming's left hand rule. Right? When it current carrying conductor, I just giving this back. This is from book 5, but giving it back. When a current carrying conductor is placed, when a current carrying conductor is placed, in a magnetic field, it will experience a force. It will experience a force. It will experience a force. First up, the direction of this force is given by Fleming's left hand rule. Do a little sketch and see if we can work out number one. The direction of this force is given by Fleming's left hand rule. Direction of this force is given by Fleming's left hand rule. I look a little bit up here. The first finger, yeah. Right, I'm going to join the board, right? For those who not see it. All right, so watch here. Right, I'm gonna help you with the first one online. And let's switch to the camera, right? Guys, come to this. What's up? Say no, come. Let's say no. Huh? Oh, for it? Yeah. What I do? I don't know. Well, and they will do it.
Yeah. Right, like you can pause a little bit. Make sure it gets you got
Alright, so watch here. Which one I gave you this one, eh?
Yeah.
Right, so watch here. So to use Fleming's left hand rule, real simple. Thumb, direction of the force, that's what you're trying to find, right? First finger, magnetic field, middle finger, current direction. Okay? So all you're doing here, you're lining this up, right? Current direction. That's what? Out. Magnetic field is what? Down, right? North to south. So this finger has to point down. So you're leaving this finger as it is, and you're pointing downward. Right? See nice? Huh? Trying to find where the thumb going. Right? So your magnetic field, north to south. Right? Magnetic field, north to south.
Oh, wait, that's
Current coming out. Right? Left hand over there. So therefore the force is where?
Left to right.
So the force is here. I mean. All right, watch. There's the hand, right? So the magnetic field north to south. So this finger going down. Current coming out. So your middle finger pointing out of the whiteboard. So your thumb going that way. Yeah, like how you have it there. So your thumb going that way. Dot. And the first thing you write, if you will sit down. Right, wait, but now you remember how the magnetic fields behave. Why this happen? Huh? No, nothing moving. Right? The reason is that when the field lines interact, there's a buildup of field lines here. And there's less field lines here. So if there are more field lines here, what will happen? Push it this way. All right? So what you have to do for me, do B, C, and D and joy diagrams as well. Do B, C, and D and joy diagrams as well. Huh? Right, you cannot get in halfway. The one box. It was one. And then understand the one. Right, so while we're here, I want you to think about, do finish, right? Think about what influences that force being exerted. What influences it? Two things influence it, right? I want to make the force larger or smaller. What are some of the factors affecting it?
Yes, I think we mark this.
Huh? Whether it's a chunky or less, why somebody had it. Go with our money. Wow. Well, it's not. Ready?
So the second one is the same thing, same direction.
I don't know.
No.
I don't know. Oh yeah, draw them out. See if we can finish up. Online, you're done. Right, next one. Magnetic field going up north to south. X means what? In. So therefore the force is to the right again, and the field lines look the same. Right? There's a build up here, and there's nothing here, right? Right? Oh, I forget to put the arrows north to south. North to south. Right? What about here? What you got here? Up. Up. What you got here, Lilia? Up or down? Show me that. Shift around. I'm gonna see line it up just like here. You just can line it up. Magnetic field north to south coming out of the paper, so the forces up, right? Yeah, so do it right relative to your screen. So it'll be like this: magnetic field north to south, right? Dot means current coming out, and the force is upwards. Again, how will you feel? Where will be the buildup of P lines underneath, right? I enjoy it too smoother, so although just stick this more, right? What about D, Shivish? What you get for D? Up, down, down. Right? So north to south, current coming out of the arm. This is current coming out of in X in, right? So the magnetic field north to south, current going in. So my middle finger pointing in. So therefore the forces down. Right. Question. What are some of the things that would affect that force? What do you think? What do you think the force is proportional to? The what? Separation between what? Strength of the magnetic field for sure, right? Let's go with things like that. Strength of the magnetic field, right? You all didn't do this quantity as yet, but one of the but that quantity is called B. It's called magnetic flux density. That is defined as the strength of the magnetic field. What else? What else do you all think will increase the force? So if I increase the strength here, F will increase, right? What else? Current here. If we increase the current in the conductor. Anything else? You mightn't see this one, What is the length?
Yeah.
The length of the conductor, right? The length of the conductor, right? This is current in the conductor. And one more thing, you all will recognize, huh? And theta, right? You all will recognize that every time we use this law, everything was perpendicular to each other, right? But if the magnetic field and the conductor are a next angle, let's say 75 or 80, it'll still experience a force, right? But you wouldn't be able to use the law to get the direction of the force, but it will still experience a force. So the angle between these two is important, right? If the angle is 90, you're gonna get the maximum possible force, right? That's why F is proportional to sine theta. When theta is 90, F is maximum, right? When theta is 90, F is maximum. Right? And when theta is 0, what will happen? What do you think will happen if these two parallel? What do you think will happen if the direction of the current and the direction of the magnetic field parallel? What will happen? Huh? Nothing will happen, no force. Right? Because watch this here. If theta is 0, sine theta is what? 0. So the force is 0. Right? So what that means now, what all this brings together for us is this. F is equal to B I L sine theta. Right? That's the force exerted on a current carrying conductor in a magnetic field. Okay? And it's the length of the conductor. Right? So make a note, of course, that when theta is 90, the force exerted on the conductor is maximum, right? Make sure you have that, right? Okay, so again, to find the magnitude, we use this formula. To find the direction, we use left hand rule, right? Okay, so when they ask you for direction, left hand rule. When they ask you for the magnitude, this formula here. Okay, all right. Let's just try this more question here. All right. Just now give you a calculation. I just want to talk about magnetic flux density, right? See this here? You see this new quantity? This quantity is just like you all remember electric field strength or gravitational field strength. This is like the magnetic field strength, right? So the strength of the magnetic field is given by this here. Okay? So the strength of the magnetic field is called the magnetic flux density. All right? So if I wanted to find magnetic flux density, right, we can kind of just rearrange this, right? we can say that magnetic flux density is F over IL sine theta. Okay, that's a simple relationship that we can use, right? F is equal to, sorry, B is equal to IL sine theta. Right, and let's going back to the handout. The force of the current carrying conductor, the force exerted on a long straight current carrying conductor placed in a magnetic field, other than its own, depends on those four things, right? You all agree with those four things? Yeah? Should be, that's why I'm sending the message. You get a send if you agree with these four things there. Huh? What's the four things you're looking at again? Right? You sure?
Yeah.
There's an error in one of them. Can you tell me which one has the error? Which one has the error? One have an error in it.
Still one thing.
Ah, okay.
Yeah.
You going now? You going?
I did it download. I was started. No, get it. No, was he doing no? Yeah, well,
Right, yeah. So the magnitude of the current will control the force. The length of the conductor will control the force angle between them and the strength of the field. Okay, same four things you talk about, right, Nicola? All right, so what's here? What is magnetic flux density? Right, of course, we're learning the definition. The magnetic flux density of a magnetic field is defined as the force, right? And let's take the same formula, put it in words, right? Right, is the force per unit current on a current carrying conductor, which is perpendicular to the magnetic field. SI unit is what? What's the SI unit short? Huh? Tesla. Right? Capital T. Yeah.
hey, that's
When I see the first time, I put those out. Right? Yes. So Tesla, right? That's the SI unit for magnetic flux density. And the definition, the Tesla is the magnetic flux density. Sorry, the Tesla is the magnetic flux density of a field which exerts a force of 1 Newton per unit length per unit current, and a current carrying conductor which is perpendicular. All right. Except for that, you can ignore that there, right? Everything else okay. Perpendicular. Oh, so theta is what? 90 and sine 91, right? So we can eliminate sine theta by doing that. So 1 Tesla is equal to 1 Newton per meter per ampere. All right. Everything that comes from that definition. Right. So here we have an example of a solenoid and magnetic fields around it. Right. There is a quantity that we're going to learn later on called magnetic flux. So here and here, same area, right? But what you recognize, they have what you recognize different between them. Look at the circles, same area, but look at inside the circles. Right, different number of magnetic field lines. You see enough? So the first circle has more magnetic field lines per unit area. The second circle has less. Right? So the first has higher magnetic pull-up. Alright. And the one below has smaller magnetic flux. Okay? Magnetic flux symbol is this. It's given by magnetic flux density by the area. Okay? So the more field lines you have in a particular area, the bigger your magnetic flux. Alright? So otherwise to mix up flux and flux density. Any current symbol? What did it say?
Actually, line is going.
Yeah, that was like what is right? Then all right. I just want to change the scenario that we have on board, right? And I want you to see if you can develop a little formula. So I want to change the scenario on board. Well, not you. I want to change the scenario here. If I were to place a conductor in a magnetic field and experience a force, right? Correct? But what would happen if I have a little bit different? If I were to place a charged particle. If I place a charged particle in between there, what do you all think will happen? So I'm taking a look at a force. I'm taking a look at a force on a charged particle in a magnetic field. Right? So I have a magnetic field, I have north, and I have south, and I have a negative charge. Actually, let's make it positive. A positive charge going this way. What do you think will happen to that positive charge? Anything at all? Think about it. It'll experience a magnetic force, right? And what you need to remember, in a current carrying conductor, right? Right, sorry. Right, so it's moving this way, right? So the positive charge moving this way. All right, wait, just now. Why just not working? Right, okay. Just had to represent. But what you see? So if I have a charged particle moving this way through a magnetic field, right? This charged particle will experience a force, right? And the way you work it out is like this. You remember what this finger was again? Current, right? And the current direction of a what? Positive particle, right? And that's conventional flow. And this is conventional flow. So this is the direction a positive charge will move in. Okay, so watch this here. If I apply that here, what you will get? Magnetic field, north to south, right? Magnetic field, north to south, right? Current direction going that way. Then there's a force exerted going. You're going into the paper. I can't really draw that so good, right? but I will draw into the paper something like that. Right? So the force is into the paper. Right? So again, the positive charge is the direction that the current will go in, right? So the current direction is the direction of a positive charge moving. So the positive charge going that way, right? North to south means that the current going. That's okay. Current go magnetic field going down, and the current direction is towards me. So therefore, the forces into the whiteboard or into the paper. See that? Nalia? All okay there? You guys, can you mind looking up here? Yeah. Right? So the force is inwards. All okay with that? So what we need to develop now is that we know that F is equal to BIL, provided that theta is 90, right? And the theta we're using is 90. I want to figure out a formula now that would allow me to find the force on this charged particle. Any ideas? Let's say the particle moving with a velocity v. So I applied a particle with a velocity v inside here. Any ideas? What we can do? So I want to get the force exerted on this, but I have to bring in Q and V. So I have a particle moving with velocity v. Huh? What's that? Capacitance? No capacitance here. Huh? MV. MV? What you just remember anything? So, all right, think of a formula that has Q and I in it. Q is equal to? So Q is equal to IT, and I is what? Equal to? No, Q is equal from this formula. Q and T, right? So can I replace this I? So I'll get F is equal to BQ all over times what L on T? Speed, right? So it means that F is equal to BQ. Right? Put lowercase v because it's not voltage, it's velocity. All right? So therefore, the force exerted on this positive charge is given by that. Right? Copy it down. While you're writing, I want to ask Ariel something. Are you ready one time? Yeah. Who? What's your name again? Yeah, Ariel, you ready? Yeah. When you ready? I'm going to leave them. No, Miguel there. And somebody else, I'm Miguel. She don't know. Yeah. Ready now? All right. So, Arian, what would have happened if there was a negative charge? If this was a negative charge going this way, what would happen? Would the force have been in or out? Huh? If it was a negative charge going this way, right? Would the force be into the whiteboard or outside the whiteboard? Out wide. White opposite. Right? So what you have to remember is this, very correct. What you have to remember is if a negative charge going this way, then positive charges going the opposite way. So therefore, this finger will point towards me. Magnetic field north to south, going down. Therefore, the forces out of the arm by God.
Say, please. It's right.
Now,
Okay.
right hand rule is kinda, but no. They're using the same rule, but just changing direction. This current direction is direction of a negative, of a positive charge. When you use right hand rule, it's more for generator and it's used to current. So it might coincidentally, it might work out, but that's not what you use it for. So when it's a positive particle, the direction is the direction that it's moving in. When it's negative, it's upwards. All right. So underneath this, right, note that in Fleming's left-hand rule, note that in Fleming's left-hand rule, note that in Fleming's left-hand rule, the direction of the current, is the direction that a positive charge will move. The direction of the current, the direction that a positive charge will move. All right, let's try some small examples. Example 1. Find the magnitude of the force. Find the magnitude of a force, on a conductor. Find the magnitude of the force on a conductor of length 0.3 meters. Of length 0.3 meters. In a magnetic field. In a magnetic field of strength 0.2 Tesla. Of strength 0.2 Tesla. At an angle A, part A 90 degrees, part B 30 degrees. Yeah, 90 degrees, part A, and part B is 30 degrees. Did I give you the current value? Oh, I left out that 4 amperes. Current strength 4 amperes. That is B is 30 degrees. B? Part B is 30 degrees.
No, B is equal to 0.3.
Yeah. Conduct, yeah. Need to use this one. That would be cultivation. Can I try to punch it? Who are them? What you got? What you call it? Ah, no, wala kayo, hindi ko yung take a leave, hindi ko yun. What I said B was again, right? And I gave you a conductor. I gave you a conductor First one is perpendicular, right? So the angle is 90. And the current is how much?
4.
Current is 4. And the length of it is? So the length is 0.3. Right? So that's the first scenario that I want to find F in. So F is equal to BIL sine theta. B is 0.2. I is 4. L is 0.3. Sine 90. How much you got here? 0.24 Newton. Okay. Next scenario. Other scenario is when it's at 30 degrees, right? Everything is the same except for the angle. I change the angle only, right? So that F is equal to 0.2 by 4 by 0.3 sine 30. Right? Sine 30 will give you half of this. 0.12. Yeah, 0.12. All right, next one. Work out this. Right, I'm giving you a charged particle moving in this direction. 2 by 10 to the 6. 2 by 10 to the 6. And the angle is, let's keep it simple. The angle is 30 degrees. Right? Same flux density, right? Right, the particles are electron, eh? Sorry. Right, the particles are electron, right?
Wait, yeah, she got.
Trying to find the force. Right, same thing, the force exerted on it. Trying to find the force exerted on it. Huh? Use what? The electron. Huh? No, what's the charge of an electron? 1.6 by 10 to the minus 19. Right? Yes, so in case you didn't know, right?
Let's give it up.
Yeah, just give it up. But right now you don't know it, so I'll give it 1.6 by 10 to the minus 19. Right? Find the force exerted, right? Right, so what we got here? F is equal to B cubed V, right? And the B is 0.2, right? Question. Is it BQB or BQB sine theta? Sine theta because of an angle, right? Right? So, Kavish, what are you doing now? How much you got? What? So Q is what? 1.6 by 10 to the minus 19. P is how much? Right? 2 by 10 to the 6 sine 30. Right? So what you get there? 3.2 by 10 to the minus 40. That's okay? I know I rub it off, right? But there is something I wanted to always notice about this part, right? What you would always notice, right, is that if I were to try to apply the rule, let's focus more on the one that's 90, right? If I were to apply, have a current carrying conductor here, sorry, have a magnetic field and have a charge going this way. You can do me a favor, find the direction of the force here. It's moving this way. X is the magnetic field. X means what? Magnetic field going in. X means in, dot means out. So the magnetic field here going in. I wanted to determine direction of the force here from. Okay, so there. Find the direction of the force here from. I'm wrapping this up, right? Yeah, sorry. We all get? The force is where? So it moving that way. So remember a negative charge going that way. So a positive charge going the opposite way. Right? So the direction of current is this way. X means what? It's going into the paper. Therefore the forces what? Down, right? wonder if I can get a simulation to show you this, right? Do the same thing here. What will happen here? How it will move here? Right? Magnetic field going in, the negative charge going that way, so the positive charge going towards me. Right? So current direction is towards me, and the forces upwards. Right? But here's what we're trying to really map out, right? We are trying to map out Arian. Watch here, right? We are trying to map out Nolia. We're trying to figure out how that electron, how this really going to move here on. Hey, all your watch here. This is all on your phone. Tell me what, think about this charged particle, right? It's moving this way, but it have a force being exerted on it inwards. What do you think the path will look like for that electron? If I allow it to just continue to move in an electric field, what will the path look like? What's that? And also it will come down here. So the force is down, right? It be what? Think about it, like giving you a few minutes. The question is we're trying to figure out the direction that the force, sorry, that that the force will cause this electron. What part the electron will follow? So you want to know the path of this electron. Would it be straight line? Would it be curve? Would it be diagonal? Would it be same conditions? Same conditions here. It's moving in, right? It's moving in just like this with a velocity v in a magnetic field with this direction. You want to figure out the particle follow. Now, I want you to remember this, right? What you all recognize there about force and velocity, Devish? What you recognize about force and velocity in example A and B? They have something in common. Perpendicular. So they're always perpendicular. Think of something that you would have learned in unit 1 or 4.5 that always has the velocity perpendicular to the direction of the applied force. Not formula, a direction. Something that's happened. Something behaves like that all the time. Something behaves in such a way that the force is always perpendicular to the force is always perpendicular to the velocity. Because no matter what happens here, these two things are always going to be perpendicular. So even if it's moving upwards, as it moves, these two things perpendicular. But of course, we know direction will change a little bit, right? But think about it. Think about something that always has, I'm trying to give you a hint here. Something that always has the velocity and the force perpendicular. Something that always has the velocity and the force that's perpendicular. That is circular motion. Right? Circular motion. So if I were to try to map it out, that's not circle. That's not circle. Huh? Right? So when the particle here moving in this direction, the force is in this direction. When the particle here is moving towards its center. When the particle here is moving towards its center. When the particle here is moving towards its center. So what does that mean? What that means is that the path that electron will follow is a circular path. Right? Remember, it's a kind of 3D thing, right? So I can't really draw it too good here. Right? But one thing that we'll always know is that the force and velocity always what? Perpendicular. Regardless of how it behaving, the perpendicular. And if that happens, then the path is circular. So the path of that electron is circular. Okay? So yeah, remember your circular motion formulas now. Yeah, I'm gonna give you a question one now. Yep, there's the answer. Yes, so yeah, remember. That's good. I really can't help you there. Everybody okay with that? Right, so you join it like this, huh? You join A, B, then C. Right, you come in this way, right? A, B, then C. You join A and B, and then you join C to say that the path is circular. And then I'm going to ask you some things on circular motion. So you have to remember your circular motion, and I'll go with Vanaya and then short. Monthly night. Right? So the part that this will follow is what? So watch, even if it's 30 degrees, it don't matter. The velocity is here and the force is perpendicular to this. Okay? They're always going to be perpendicular to the path of the circular. Huh? Stop, like, forget.
Yeah, that's the idea.
Nah, finish this. Nah, I'm not going to remember nothing on this tomorrow, so I'll finish it out. Huh? Okay, all right. So here's it. If Nikolai answer, we finish in class. What is it that you open Naya? Right? So we said that the path is circular, right? Yeah? So anybody, Nikolai or Vanaya, what provides the centripetal force? The centripetal force is what? Half mv squared. What is the force supplying the centripetal force? What allows it to go in that circle? When you see tension here, apply to what we've been doing, right? And don't tell me velocity. Yeah? How can velocity be a force? What provides the centripetal force? Huh? Okay, in this diagram here, what's supplying the centripetal force? F. F, right? And what type of force is that? A magnetic force. A magnetic field force. So centripetal force is the magnetic field force. Right? So the magnetic field force is what?
BIL sin theta.
BIL sin theta. For charged particle. That's what we just learned. And you want to finish class early.
BQV.
BQV.
Yeah,
All right. That's our electron. I look like theta now. I'll leave it as kids. Right? What's the formula of centripetal force? What's the formula of centripetal force? We will again, that's kinetic energy.
And omega square R.
M
Omega
omega squared R.
square.
M omega squared R is equal to, okay? And then we can manipulate and find anything we need. All right? So what's important here, Nalia, for you hold your head, right? Remember that the centripetal force for this electron is provided by the magnetic force on the electron. Okay? This is the magnetic force on electron. Right? So we could use this version, or I was really hoping to hear this version, mv squared on r. That's the one I was looking for. If I heard this, class was done. All right. So mv squared on r. That's the one I was looking for. Right? And then you can rearrange what you need, right? So if I ask you to find period now, period is what? We don't have F here. Right? So 2 pi on omega. You have to remember your circuit here. You have to remember your power. Remember when we did a charge in our electric field, you had to learn parabolic motion. So you have to learn your parabolic motion and your circular motion. Circular motion. All right, one question and we done. Well, it should come up.
I can't.
Couldn't switch it. That's how the labs and all kinds of things going on.
Forget no.
Yeah, like, outside.
I can send a picture of my alarm.
They have a lab. Why? What? That's at 2 o'clock. 1 o'clock. Huh?
Yes, check it out there. Yeah.
So the end of that. All right, last thing on we done, right? One question and you finish, and I'll give you a break, right? For pure.
How long then? This class early, can't get a lot of it.
About class after.
Anybody class?
They're online, yeah.
Exactly, the
All right, part of an electron. Next one. Question 1. There's one question and we done. The part of an electron in a uniform magnetic field. Just one question and we finish, right? The part of an electron in a uniform magnetic field of flux density the part of an electron in a uniform magnetic field of flux density 1 by 10 to the minus 2 Tesla. 1 by 10 to the minus 2 Tesla. In a vacuum is a circle. In a vacuum is a circle. Is a circle of radius 1 by 10 to the minus 2 meters. Is a circle of radius 1 by 10 to the minus 2 meters. Calculate the period of the orbit.
Very sticky, yeah, very sticky. That's the one on the list. Apa sebab tu? That's what I'm about.
Find the what it says?
The
Right, find the period of the oven.
so all they give is just see radius and the
Yeah, plus density. And you charge it by electron, right?
flux density. I get idea.
Huh?
Idea.
Well, the plus there as capital B. Yeah.
So flux density is BA. Now I think flux density is BA.
Right? Just to make it a little better for you, and I will use the next version to help you, right? The next version I could also use is M omega B. This might help you. Right? Because it might, I just do think I'll do figure out our next part here. Try this version. Right? And see if we can find period is what? Period is what? Period is 2 pi on omega. So you need to find omega. All right. So you remember what Q is? Q is 1.6 by 10 to the minus 19. What's the mass of an electron again? What's the mass of the electron? Am I remember? Okay, let's check the front of the pathway.
I think that's one of my
Something like this.
9.1. Let's check and make sure people.
9.1. I can be
9.1. Okay.
9.11.
9.11 by 10 to the minus 31. Try this, Neil. See if that will help you. Use this relationship here. Don't worry with this. I'm not sure if all will see that something happening here, right? So use this version. Remember simple. Remember circular motion at 3 versions, right? And I gave you all 3 here, right? See if you can find omega. Oh, yeah.
Beginning what this one time. Within times.
No, I just gave you a radius and something else.
It don't be and then it made us then we just yeah.
No, you have a next part because we don't need it. You have a next part, but I didn't give it. Right, so hopefully you reach here, hopefully you recognize that the B's cancel. Right? And you recognize that because the B's cancel off, you get omega to be B, Q, and M. Right? And once you get to omega, you can find T. Right? What was B again?
1 by 10 to the minus.
1.
Like 10 to the minus.
That was B, right? Q is 1.6 by 10 to the minus 19. And M 9.11 by 10 to the minus 31. That will give you omega, which is 1 point. Right.
Something wrong like that.
By 10 to the power 9.
1.4.
Right? Remember that's rads per second. And then find T. T is 2 pi over 1.76 by 10 to the 9. Right? So I'll take the omega and I'll find for T. I'll try it again. Three point. Right? 3.58 by 10 to the 9. Huh? I forgot the. Everybody clear it up? Yes. So that's it. All right. Right. So that's the beginning of magnets. We'll continue next day, right? You're coming on Saturday, right?
Yeah.
No?
No. They're coming. That's yeah. I will. Sit. I have that. Lunch to go to there. They're all watching down.
That's for real. I'm not coming Saturday.
For real.
You coming Saturday? Let's show by hands now. All the liar. Yeah, then Nikolai got probably thought he had to go away. Yeah. Oh, they have it. One of them out. All right, so the quality is not coming. But not coming to pure match. Huh?
It's fine.
You already not coming Saturday? Thursday? All those set them up now.
I mean, so for you.
I'll message on the group. But most likely I might do that. Yeah, well, you could run, well, you can just log in, that you know where. They won't be here Saturday.
So we can't sleep last night.
I was going to Thursday.
When the people that say I'm not too much for
All but nobody comes Saturday. That's
Worry. Since when